everybody, and welcome back. Today we're going to be going over Unit 2, Lesson number 5, which are earthquakes. So far we have talked about how earthquakes occur along transform boundaries. So that's where two plates actually slide past each other, and that is where we get earthquakes. So we're going to just dive a little bit deeper into talking about what actually are earthquakes and what causes them. And so, as always, you should have downloaded your interactive notebook pages for today, and we can just jump right into it. So what is the actual cause of earthquakes? Well, earthquakes are just vibrations of the Earth's crust. So when we think about the lithosphere, it's just kind of the shaking that happens in the crust. So this usually occurs when rocks under stress suddenly shift along a fault. So we're talking about at like transform boundaries where fault lines are made and the rocks are shifting, causing this vibration. Earthquakes are caused when plates overcome friction and move. So there's something we need to know about called the elastic rebound theory, and this happens when an earthquake occurs. So step 1, stress will build up between two plates that are locked in place by friction. Okay, so the plates are moving past each other and they're kind of locked in place, so the stress just kind of builds and builds and builds. And eventually we'll get to step 2, which is where the plates will overcome that friction and it will cause a shift in the plate. So the plates will actually move, and this movement will create those vibrations, which we know as an earthquake. And then finally, the plates will snap back to their former shape. So we got those 3 steps. The stress kind of builds up. The rocks are initially locked in place. They're not moving. And then once they can overcome the friction, the plates will move, cause the vibrations in the earthquake, and then they'll snap back to their original place. So here we've got our rocks on each side of the fault. So they're moving because what's causing this movement? Again, convection currents in the mantle that are causing these plates to move. The rocks are locked, so they will bend a little bit, storing energy, and then the rocks will eventually let go and spring back, and this will actually cause the vibration of the earthquake. So there are different parts of an earthquake we need to know about. The focus is the point on the fault at which the first movement occurs. Okay, so this happens within the earth. The epicenter is the point on the surface directly above the focus. So epi means above, and when we say above the surface, that's just above the focal point. And we have to be able to look at a diagram of these and be able to pinpoint the focus in the epicenter. So here we have our fault line. Here we have our footwall. Remember, we can tell our footwall by it's a larger than 90-degree angle. So we have our footwall and our hanging wall. So this is our fault here. And our focus is on the fault line. Okay, so our focus is here beneath the surface on the fault line. This is where the earthquake starts. The epicenter, epi means above, the epicenter is on top, right above the focus. So the vibrations that are created from an earthquake are known as seismic waves, and they radiate out in all directions. We've talked about seismic waves a little bit, but we're going to get into them even more here. So there are 3 types of seismic waves. The first is the P wave, which is a primary wave. And this is a motion that compresses and stretches materials. It can move through solids and liquids. This is very important. So P waves move through both solids and liquids. They will be the first waves recorded by a seismograph, and the seismograph is just something that records the waves of earthquakes. We'll talk about that in just a second. S waves are secondary waves. They move in a side-to-side motion, and they can move through solids only. So S waves cannot move through liquids like P waves do. And these are the second waves recorded by a seismograph. So the S waves are important, and this was something we talked about when we talked about the layers of the earth, but it's going to be a little bit more pertinent to you now. So remember, when we talk about the core of the earth, the inner core is solid and the outer core is liquid. So the outer core of our earth is liquid. Well, remember I said, how do we even know that the outer core is liquid? Because there's no possible way for us to drill down into the earth and see it. We just don't have the technology. It's too hot. Well, we know because scientists can monitor these seismic waves. So I told you there were S waves, which are the secondary waves. Again, they can only move through solids, so they don't pass through liquids. So when they measure these waves in the Earth, they find that these S waves are deflected around the outer core because they can't pass through them. And if the S waves can't pass through the outer core, that means that the outer core is liquid because S waves can't pass through liquid. Okay, so that's how we know the outer core is liquid. So the primary and the secondary waves, when they reach the surface, they become L waves or surface waves. And these are a rolling motion, and they can only travel on the surface of the Earth. So these are not deep within the Earth. These are the last to reach the seismograph, and they're slow moving, and this is what causes the most damage. So when we think about buildings being broken, sidewalks being cracked, things like that during an earthquake, the L waves are what is causing the damage. So P waves travel twice as fast as S waves. That's why they're primary. So on a seismograph, we'll get the P waves first, then the S, then the L waves. So here's a depiction of the different types of seismic waves. So we have compression waves, which are the P waves. So they'll kind of compress as they move along. And there is a video I'm going to show you guys too. It'll be linked on your lesson for the day. The S waves are kind of a side-to-side movement, so they'll have more of a typical wave shape when we think of like the wave at the ocean. And then here, the L waves that make it to the surface that cause all the destruction, we can see they're slow moving, but they also cause all this movement. And this is what cracks and destroys buildings and property at the Earth's surface during an earthquake. So a seismograph is an instrument that detects and records earthquake waves. It records the up and down motion. It records east to west motion, which is side to side, and north to south, which is also side to side. It locates and measures an earthquake, and seismographs can tell how far away the epicenter is. So where is the epicenter of the earthquake? Remember, the epicenter is located directly above the focus where it starts. So if you can find the epicenter, you can find where the earthquake has originated from. You have to have 3 seismographs in order to determine the exact location. So you have to have 3 of them. The seismographs are also used to determine the strength of an earthquake. So here is what happens. So we have the horizontal motion being measured. You've got the rotating drum that will have paper on it that you can record, a pin with a weight and a spring. So as those waves make their way to the surface, and as this begins to move back and forth, it will swing in response to the waves that are being measured. So again, the P waves make it first, then the S, and then the L waves. So here is an example of what a seismogram might look like. So we've got that pin on the ball, and as the P waves arrive, it will start to wobble back and forth. Then a short time later, we have the arrival of our S waves. Then we have the arrival of these slow-moving, very destructive L waves. They're also known as love waves. And then there are 3 of these because, again, in order to find the epicenter, you have to have 3 different seismograms to plot the point of the earthquake. And here are examples of that. So you would have a seismogram here, here, and here, and they would plot the points, and you could use that to determine the epicenter of the earthquake. You guys won't have to do that with the 3 circles like this. We just need to know what the epicenter is, and that we have to have 3 seismographs to be able to determine the epicenter. This is a graph that can be used for determining the epicenter distance. So it says, suppose a seismograph at an earthquake monitoring station recorded the S wave from an earthquake 4.5 minutes after it received the earthquake's P waves. Based on the graph, approximately how far is the earthquake's epicenter from the monitoring station? So here we can use this graph to determine the epicenter distance. So we've got epicenter distance in kilometers on our X, and we've got travel time in minutes on our Y. If we look here, this first line is our S wave. That'll be reaching after the P wave, and the P wave is on the bottom. So it says that the time between the S and the P wave is 4.5 minutes. So what we can do here is find at which point there is a difference of 4.5 minutes between our S and our P wave. So if we look over here, 4.5, these are in increments of 1. So 1, 2, 3, 4, 5. And then it's 4.5, so it's going to be between this 4 and 5. So this is kind of the length we're looking for, right? We're not going to follow it directly over from this point. If you do that, you'll get messed up because we want to find where there's 4.5 lengths between the P, or 4.5 minutes between the P and the S wave. So if we look here, let's see here. We've got 1, 2, 3, 4. That's almost there. 1, 2, 3, 4. So it's going to be somewhere around this area because this is where there's going to be a difference of 4.5 between your S and P wave. So if we follow this down, we can estimate roughly the epicenter would be between 32 to 3,300 kilometers away. Now, if we were in the classroom, we could use a compass. So you guys know the little like circular compass that has a little pencil in it, and you can do this with much more accuracy. But just as a rough estimate, we're just looking to find the difference between the S and the P wave. So find where there's a 4.5 minute difference, and then follow it down to your x-axis, and you can find the epicenter distance. The Richter scale measures the magnitude of an earthquake, and this is just the amount of energy that is released. So seismograph measures the waves. The Richter scale measures the magnitude, and it's a scale of 1 to 10, with each number representing 32 times stronger than the previous number. So a 10 would be the largest magnitude earthquake that you can have on the Richter scale. The Mercalli scale and the Rossi-Forel scale are used to measure the intensity of the earthquake, and this is usually measured upon observing the damage done. Now, I will say you guys will have a quiz question that asks about what is used to measure the intensity of an earthquake. It's the Mercalli scale. Okay, the answer is the Mercalli scale. And that is it for earthquakes. We are going to do a little bit more reading about this. And just keep in mind that these are occurring at faults, typically along a transform boundary where two plates are moving past each other. So that's all I have for the note portion of this lesson. If you guys have any questions, feel free to email me and let me know.